a lot of water pressure. It works like this. The pressure at the top of the dam is lower than the pressure at the bottom. That's why this one squirts out farther. So we put the turbines, the things that make electricity, down here. A lot of pressure makes a lot of electricity. This is a big dam. It's Hoover Dam. It all works with pressure, water pressure.
My name is Patrick Stifter. I work for a water jet shop. A water jet can cut through wood like a hot knife through butter. And a granite slab, no problem. Water's put in there under a pressure of approximately 60,000 pounds per square inch. Under that pressure, that water is traveling at Mach 3. That's like 3 times the speed of sound. Even strong metals like titanium, which are used in airplanes and spacecraft, can be cut with a water jet. The high pressure water enters from the top, goes through the carbide at a very high speed, which draws the abrasive or the sand that we cut with through this white tube. The water accelerates the sand, producing a cutting tool.
Moments in science. Dateline, the dartboard. A penny saved is a penny earned, but not when it comes to darts. The penny's pressure spreads over too large an area. No trick will make it stick. Here's a tip. A darts tip focuses pressure on a point. Stick with darts. They stick in the board. Isn't she sharp?
It's hard to compete with Bill Nye's energy, but my production crew's a lot less. Before we get into converting pressure units, I want to review kinetic molecular theory. As we study gases, we're looking at a particular phase of matter that has certain characteristics. You would say this is the gas phase. It's well noted that the atoms are moving around a lot faster, and I can give them some more energy, but we're looking for a straight line motion and not connecting to each other. This is a key aspect to what is an ideal gas. An ideal gas is small, does not bond to other gas molecules, moves very fast in straight lines. You have to think of billiard ball collisions. The energy is not lost in the collision. When there's condensation and the molecules lose their energy, they are able to clump together in the liquid phase. The liquid phase, we're saying they can make and break bonds between them, and I'm using bonds a little incorrectly there. The official word is intermolecular forces, but they are between molecules or between atoms. You have some interactions, but they are moving around. But liquid is a very dense phase relative to gases. See, gases are not dense, and because they're not dense, we will need to discuss pressure as part of the gas descriptors, because gases can be compressed. This spacing between them can be eliminated. Finally, let's look at the solid phase. And in the solid phase, we see vibration only, tightly packed, not subject to pressure changes because there is no spare room between them. Here's a summary slide of the kinetic molecular theory. You have a good image on the right of a gas molecule, but gases are mostly empty space. They are in constant random motion. They neither attract nor repel each other, and pressure is due to the collisions of the gas particles with the container walls. And here's a formula that we won't be needing until later, but the important idea is that their energy is directly proportional to the temperature. In particular, for gases, we need to work in Kelvin temperatures because we have times when we need to divide by the temperature, and we can't be dividing by 0. I want to introduce you to one term that shows up a lot when we work with gas problems, and that is the standard temperature and pressure. It's not STP oil, but it is 0 degrees Celsius for the temperature, or 273 Kelvin, and a pressure of 1 atmosphere. So sometimes you'll see what is the new volume at STP, and that's code for this temperature and this pressure. Because the gas phase is not dense and gas molecules are spread out, we need to specify pressure when we're talking about gases. Now, most of our experience is at atmospheric pressure, where things are not pressurized, we would say. But for gases, you need to think of pistons and engines, and where the gases can be compressed. So, unfortunately for you, there are lots of different terms used for pressure. First of all, let's define pressure. Pressure is defined as force per unit area. And on the Bill Nye video, this is best expressed by the girl who was throwing pennies at the dartboard and then finally threw a dart at the dartboard. The dart was able to penetrate because the same throwing force that she had is put into a much smaller area, and so the pressure is greater and the dart can penetrate the board. Likewise, you think of a woman with high heels. Here's my beautiful high heel. We see if she'd walk flat-footed through the sand, her footprints wouldn't go far into the sand. But if she wears high heels, you'll get deep holes at the heel. Or another example would be ice skates. Here are your ice skates, and all of your weight is concentrated on a narrow blade, and it's so much pressure that it liquefies the ice underneath and allows the skate to glide. So pressure is force per unit area. And unfortunately for you, there are many different expressions for pressure, and they're all up here in this white bar. We talk about living at 1 atmosphere pressure. Since we're at sea level in Fort Myers, we are at the definition of atmosphere, which is sea level. The atmospheric pressure decreases as you go up in elevation. There's this term 760 torr, or 760 millimeters of mercury, and that refers to the barometric, or the barometer, and how it works. So here's a picture of a barometer, and it's filled with a pool of mercury, and the mercury actually rises up into the tube according to the air pressure pushing down on the pool of mercury. So if we're at the beach here in Fort Myers, this would rise 760 millimeters high. This is in inches. But for us it would rise 760 millimeters because we are at 0 elevation. And that's what 760 millimeters of mercury means. And the man who developed the barometer was Torricelli. And out of honor of him, this is called the torr. There's the British unit of pounds per square inch, and 1 atmosphere equals 14 pounds per square inch. And then finally there's the SI term of the Pascal. The Pascal is force in newtons over meters squared, and it's 101.325 pascals is 1 atmosphere. Now you have a couple problems in mastering chemistry on converting pressure units, but let's go through some examples right now. 500 torrs would be how many atmospheres, and you need to just work with your conversion factor. So I would say 500 torr and then times 1 atmosphere equals 760 torr. I'm going to multiply by that. And I'm using my conversion factor of 1 of these equals 760 of these, so I may write a conversion factor of these over top of each other because I'm basically multiplying by 1. And when I do that, I get 0.66 atmosphere. And that makes sense because 500 is less than 760, so I have a fraction of an atmosphere. If I have 900 torrs, how many millimeters of mercury is that? I look up at my conversion table. Torrs, millimeters of mercury, same thing. This is an easy problem. 0.9 atmospheres is how many pounds per square inch? Well, I'll make a conversion factor with the thing I want on the top, 14.7 psi equals 1 atmosphere. So I'm multiplying by 1 with this term because they're equal to each other. And I get 13.23 psi. I really don't have that many sig figs, but you see the math of it. And this is less than I started with, and that makes sense because I have less than 1 atmosphere. Finally, if you're given pascals and asked to move to torr, this is a 2-step conversion. Let's first get into atmospheres. I know that 1 atmosphere equals 101.325 pascals. And then let's convert to torr. 760 torr is to 1 atmosphere. And when I do that, I get 675 torr. Now I'm not really watching sig figs here. I only have 1 sig fig, but I want you to see the outcome here. Alright, so the key idea here is that there are many expressions for pressure. Pressure is force per unit area. I can convert between them by making conversion factors of the thing I want over the thing I was given. Multiplying by this is like multiplying by 1, and I can convert to the other unit. That's it for pressure units. Practice it in Mastering Chemistry. You also have a worksheet on converting pressure units, and this should give you enough practice to be good at this. See you next video.